The goal after this video is for you to be able to graph any tangent function and any cotangent function using a lot of what you know about sine and cosine. So we'll dive straight in. If you were to go to Desmos right now and graph the tangent function, you would see a whole lot of what look like x to the third functions just graphed in succession. So this is, in general, what the tangent function looks like. Once again, we're going to graph one full period. So we're going to graph initially from negative pi over 2 to pi over 2. And so I'm going to kind of focus in on just this section, and then we can replicate that. So I know, just to make a table one time, we won't do it again, tangent of 0. So that's my x value, my y value. Tangent of 0 is 0 from the unit circle. You plug in 0, get out 0, easy peasy. But this is important. Between the negative pi over 2, where tangent is undefined, you're going to draw bloop, vertical asymptote. Tangent at pi over 2, undefined. So let me write that in. Tangent at pi over 2, undefined. We know that from the unit circle. Same with negative pi over 2, undefined. So you're going to start, the nice thing about tangent is it's nice and clean. You're going to start every function between negative pi over 2. All right, here's your argument, bx plus c, and pi over 2. Now you notice I don't say less than or equal to where I did with sine or cosine. Sine and cosine were defined everywhere, so they were defined at this left boundary and this right boundary. Tangent is not, and cotangent is not. So you have undefined values. So I want all x values that are greater than this, because x can't be this, undefined, and less than pi over 2. So halfway, once again, you know I'm picky. I need 5 exact x values. One is a vertical asymptote. Another one is a vertical asymptote. So your boundaries are vertical asymptotes. Halfway between the vertical asymptotes, you have that nice x-intercept, which is going to depend on the d value. We're going to see, if I were to write plus 5, that would shift that point up 5, but we'll deal with that in a minute. So halfway between this midpoint and that boundary, pi over 2, is pi over 4. And here's what's nice about the tangent function. When I plug in pi over 4, we already know that tangent of pi over 4 is 1 from the unit circle. So pi over 4 goes to exactly 1. So that's a nice clean number to find. And it depends on the a value. A is understood to be 1. So if I put a 5 in front of tangent x, 5 times tangent x, then that would mean pi over 4, right? Tangent of pi over 4 is 1, times the 5. So now that value, instead of being 1, would be up at 5. Now, once again, we're going to see all of this in actual examples, but I just want to kind of get you ready. All right, and then negative pi over 4, just to get it out of the way. So you have 1, 2, 3, 4, 5 exact x values, just like always. Negative pi over 4. Tangent at negative pi over 4 is negative 1. Remember, we have tangent is an odd function. Opposites in, opposites out. So negative pi over 4 goes down 1. So I go halfway to the right, up 1. Halfway to the left, down 1. And I draw my curve. Now the curve should look like it's relatively flat initially, and then it's getting steeper and steeper. Same on this side, steeper and steeper. Okay? And this is actually what's called an inflection point. Think about the language that was used at the beginning of COVID. We wanted to flatten out the curve, right? So if you watch this curve, it's decelerating. The actual rate of change, even though it's going up, it's flattening out. So it's slowing down, and then after it passes this point, it actually starts to speed up again, accelerate. So this is called an inflection point, where it goes from concave down to concave up, or deceleration to acceleration So you'll hear inflection point when you're talking about economics models and such, or in this case, biological models in terms of disease. Okay, so that is one full wave of the tangent function. So the period is pi from negative pi over 2 to pi over 2. So that's another big distinction between sine and cosine, which had a period of 2 pi. Now we have a period of pi. So let's look at all of the important characteristics. I'm going to brush over this quickly so we can get to the graphing part. Okay? So the domain is all real numbers except all of these excluded values. And we saw that concept or that idea of an excluded value with rational functions back in August. So we know this function, the tangent function, is defined everywhere except at negative pi over 2, pi over 2, 3 pi over 2. So a way to write that is, if you take pi over 2 and you add pi, that takes you here. So think of that as pi over 2 plus 1 pi, undefined. Pi over 2 plus 2 pi, boop, boop, would take you over here. So any number of pi, k is an integer. K could be 1, 2, 3, 4, 5, or negative. Negative 1, negative 2, negative 3. So pi over 2 plus any number of pi is an excluded value. So the domain is all real numbers except those values. The range, remember those are my y values. This curve goes up forever, and it goes down forever, and it's continuous and connected and smooth in between. So the range is all real numbers. The period, we've already talked about that. The period is 1 pi, and then we have another period of pi, the replication, like with sine and cosine. So that's a big difference. Sine and cosine had a period of 2 pi initially. The period of tangent is pi. The x-intercepts are pretty easy. The x-intercepts are 0, pi, 2 pi. So the x-intercepts are any number of pi, where k is a whole number. So if k is 0, 0 times pi is 0. K is 1, 1 times pi is pi, and so on. Intervals of increase, so I know from negative pi over 2, not including negative pi over 2, from negative pi over 2, not inclusive, all the way to pi over 2, for that interval, from negative pi over 2 to pi over 2, my function is going up, it's increasing. And then at pi over 2, it disappears. Then from pi over 2 to 3 pi over 2, my function is still increasing. So you have all of these individual intervals where the function is increasing, and the tangent function, the original tangent function, has no intervals of decrease. The function only goes up. The function is odd, so just to remind you, odd means it has rotational symmetry, so it looks exactly the same when I rotate it 180 degrees about the origin. Odd also means opposites in, I get opposites out, and we saw that. If I plug in negative pi over 4, it goes to negative 1. If I plug in positive pi over 4, it goes to positive 1. So those are the characteristics of the tangent function, not all of which are necessary to graph it, but those are characteristics we'll see again. Okay. And just to recap, the function looks like this. So we have the same formulas. You take the period, which was 2 pi for sine and cosine. If you take the period pi and divide by the absolute value of b, you get the new period. So the period is dependent on the b value. The phase shift is always negative c over b. That shifts you left and right. And now, once again, we saw this a minute ago. This is kind of where we begin the graph. If I'm going to graph a tangent function, I do this first, right? Not including negative pi over 2, not including pi over 2, all values between, and you solve for x exactly like you solve for x with sine and cosine. Now, for sine and cosine, it was 0 and 2 pi. So you had different boundaries to begin with. Same process. So we'll see that in just a minute. All right, so let's dive into quick recap in your notes. The a value is going to make the function vertically stretched when a is bigger than 1. Okay, so if the a value is 2 or negative 2, 3 or negative 3, you're going to actually see a vertically stretched function. So this would actually mean it's a stretch, vertical. If a is a fraction or a decimal, some number between 0 and 1. So if for some reason you had 1/2 tangent or negative 1/2 tangent, that would actually be a vertical compression. So it would look like you were vertically, like you were taking your hands and squashing it down closer to the x-axis. Okay, so it's important to know a is going to make the graph look differently and what that's called. B is going to affect the period. We already know that. So pi over b, really this should be the absolute value of b. I got this from Matt Winking, who an amazing educator at Phoenix High School in Gwinnett County. He's led workshops there for pretty much, he and I started about the same time in Gwinnett County. He's a little bit younger than me, but this guy's a brilliant guy. He teaches at an alternative school, but it's not an alternative school for discipline. It's for students who, might need to work to support a family, different things like that. But he's done all online for 15 years, so he is like cutting edge with technology. So the understanding here is that b is a positive number, and we've seen that. B has only been positive. B could be negative, so if we wanted to make this a little bit more robust or accurate in terms of any function, pi over the absolute value of b. B has been positive for every problem we've done, and it will continue to be the case. All right, so phase shift, negative c over b, we know that. And then we will see, not today, but we will see functions where you shifted the function up or down. So D is easy to deal with. A is easy to deal with. The C and the B are going to be what make the graph look significantly different, and they can be frustrating sometimes. All right, let's dive into an example. All right, y equals 3 times tangent of x. Not a whole lot going on here. So the argument is just x. B is understood to be 1. C and D are understood to be 0. A is 3. So really what we're looking at is 3 times tangent of understood to be 1x plus nothing plus nothing. So C and D are understood to be 0. B is 1. A is 3. So we set the argument between, remember not including, x has to be larger than negative pi over 2 and less than pi over 2 to graph one full period. Okay, so you can hand draw these again, but I know I want 4 intervals. 2 on this side. So here's my first vertical asymptote at negative pi over 2. My second is over here at pi over 2. Halfway in between negative pi over 2 and pi over 2, I start here. If D were not 0, that would be different. Okay, but the only difference here is when I plug in pi over 4. So numerically, tangent of pi over 4 is 1 times 3 is 3. So when I go halfway over from the origin, I then go up 3 because A is 3. So just like we had a maximum at 3, now we have a point at 3. So there's half of my graph. And it should look like it's smooth and approaching infinity. And then at negative pi over 4, we go down to negative 3. Same thing, it should look like it's approaching. So we have smooth, so decelerating, kind of flattening out as you approach the origin and then going back up. Okay, and if you want to graph more than one period, absolutely. You can graph more than one full period on both sides, completely up to you. So you can graph more than that, but one full period is fine. 1, 2, 3, 4, 5 x values within one full period. I have the y values that matter in terms of making a sketch, and that's it. The period is still pi. The phase shift is 0 over 1 or 0. So all those values that we could find very quickly and easily. All right, let's try another example. Now, A is 1, B is 2. So set the argument between negative pi over 2 and pi over 2. Solve for x, so if I divide by 2, I divide all three parts by 2. This gives me negative pi over 4, pi over 4. X is between those two numbers. Now, negative pi over 4 to pi over 4, I have to split that into 4 intervals. So I'm not going to call this negative pi over 4. If you do, you're just going to have a really small graph kind of squashed in there, which is fine. You know, some of you have really small handwriting and much neater handwriting than I do. So I'm going to go 2 intervals to the left and call that negative pi over 4 and sketch. Remember, this is my vertical asymptote. So this will be negative pi over 4. Half of negative pi over 4 is negative pi over 8. Pi over 8. Pi over 4. And remember, I'm moving quickly because if we do negative pi over 4 plus 0 divided by 2, we get negative pi over 8. Now, my a value is 1, so we start at the origin. My a value is, now you can call anything you want 1. I could call this 1 as long as I'm consistent. That means this is 1. However you want to do that, it's completely up to you. Pi over 8 goes to 1, so you could have it going up and then blasting off, or you could call this 1 and have it flat and then blast off. So we could change that. Once again, we use pencils in math because you might start to sketch it and go, I don't like the way that looks. So pi over 8 goes to 1. And then negative pi over 8 goes to negative 1. There's my graph. Goes up, flattens out at the origin, and then accelerates. That is one full wave, and I have 5 exact x values understood 0. So label this negative 1, and there it is. All right, one more example where we see a phase shift come in. So A is 1, B is 1, C is pi over 4, D is 0 again. So we set the argument between negative pi over 2 and pi over 2, not inclusive, not equal to. Subtract pi over 4 from all parts. So we have negative pi over 2 minus pi over 4. It's negative 3 pi over 4. Pi over 2 minus pi over 4. It's pi over 4. All of these numbers turn out to be nice. We're not doing a lot with tangent and cotangent. I shouldn't say this, but it's true. We do a lot more with sine and cosine than with tangent and cotangent. So negative 3 pi over 4 and pi over 4. So I'm thinking of this as 3 spaces left of 0, 1 space right. So 1, 2, 3, negative 3 pi over 4. There's my first vertical asymptote. So this is negative 2 pi over 4, which we talked about in all the classes, perfectly okay when graphing. It's actually negative pi over 2. This is going to be negative pi over 4, understood 0. And then pi over 4 is my other vertical asymptote. Halfway between my asymptotes is my x-intercept. Because d is 0. If d were 1, it would actually be up here. A is 1, so I go halfway over and up 1. Here's negative 1. So here's half of my graph. And then left 1 from the x-intercept, left 1 over 1. Left pi over 4, down 1. Boom. So there it is. Nice smooth curve, decelerating, accelerating. There's my point of my inflection point. And there we go. So that's tangent. Tangent's not bad. Once you've already learned all the tricks of labeling the x-axis and solving for x, tangents actually seems easy because we've laid the groundwork with sine and cosine. So now, just to know, tangent, there it is. Cotangent, very similar. So I'm going to do a whole lot of comparing and contrasting. Cotangent does not go through the origin. Cotangent goes through pi over 2. Cotangent of pi over 2 is 0. Also, the function is decreasing instead of increasing. So here's 3 pi over 4. 3 pi over 4, instead of going up 1, 3 pi over 4 goes down 1. And pi over 4, instead of going down 1, it goes up 1 because this function is decreasing. So you have kind of the same pattern. It looks like a reflection and a shift of tangent, which it actually is. If you were to reflect this over the x-axis and shift it pi over 2 to the left, it would be the tangent function. So you can manipulate cotangent and make it tangent, just like a lot of you noticed. You could easily manipulate sine for cosine and cosine for sine. Okay, so very similar characteristics. Instead of starting at negative pi over 2, though, now we're going to start at 0 and run to pi. So it's actually a little bit cleaner. So our one full period that we're going to sketch initially is 0 to pi. So we're going to set our argument between 0 and pi for cotangent versus negative pi over 2 and pi over 2. Okay. Almost all the same characteristics. Let's look at the ones that are a little bit different. Now, instead of our x-intercepts being at nice values, now our vertical asymptotes are at nice values. So our vertical asymptotes are now at 0, pi, 2 pi, etc. So our domain is all real numbers except 0, pi, 2 pi, etc., negative pi, negative 2 pi. Range, the function still goes up forever, down forever, and all values in between. So the range is still all real numbers. The period is still pi. Our x-intercepts are now kind of messy. So our x-intercepts are now pi over 2, right, plus pi times 0. Pi times 0 is 0. So one of our x-intercepts is pi over 2. The next x-intercept is pi over 2 plus pi, or pi times 1. And then our next x-intercept is pi over 2 plus 2 pi, 3 pi, and so on. So we saw that pattern before. This function will never increase. The original cotangent function only decreases. It goes down as you move to the right, disappears, then reemerges and still goes down. The intervals of decrease are nice intervals. From 0 to pi, for those x values, the function is decreasing. For the x values from pi to 2 pi, the function is decreasing, and so on and so on. Cotangent is also odd. So if I reflect cotangent just like I did with tangent, boop, we see the exact same graph going down, going down. So just to be clear, tangent and cotangent are both odd functions. Sine is odd. Cosine is our even function. Okay, so cotangent, also an odd function. All right, so we have the same formula for sine. I'm sorry. Tangent and cotangent have the same formulas. The period is pi over the absolute value of b. The phase shift is negative c over b, so same formula as tangent. But once again, the difference is we're going to start at 0 and run to pi. We're going to have a vertical asymptote at x equals 0, and we're going to have a vertical asymptote at x equals pi, and then we're going to graph 1, boom, 2, boom, 3. Sketch our one branch of our curve decreasing. Okay, very similar to tangent, but decreasing instead of increasing. All right, let's dive into an example. Y equals 2 times cotangent of x. All right, so let's set our argument between 0 and pi. So we have 0, 1, 2, 3, 4. So remember, you always want, if you're going to use these little grids, you don't have to, but regardless, you want between your left boundary and your right boundary to have 4 what appear to be equally spaced intervals. And if you draw it by hand, it doesn't have to be perfect. Halfway between 0 and pi is pi over 2, and that's where we're going to have our x-intercept. Now my a value is 2, so instead of going to the right and down 1, I'm going to go to the right and down 2. And there's my negative 2. There's my 2. So pi over 2, this is 3 pi over 4 pi, 1 pi over 4. So don't forget, you always label those 5x values for one full period. 1, 2, 3, 4, 5. Left and up 2, because a is 2. Just like with sine, you make it look like the slope is about at a 45-degree angle. Okay, that's going to come into play in calculus when you're trying to find the slope, rise over run, change in y, instantaneous rate of change of the function. The function is always, so now it looks like it's still, it's going down really fast. Think of the economy as tanking. It's going down, it's going down, it's going down, and it's flattening out, which is good if it's the economy. And then it's tanking more and more and more. So that inflection point. Slowing down, speeding back up. You still have an inflection point at that x-intercept. All right, so there's our graph. Let's look at another one. All right, so very similar to our tangent example. A is 1, B is 1, C is negative pi over 4, and we do not have a D value. We're not doing a lot with tangent and cotangent. So set the argument between 0 and pi. Solve for x, so I'm going to add pi over 4 to all three values to maintain the inequality. 0 plus pi over 4, pi over 4. Pi plus pi over 4, 3 pi over 4. So now, pi over 4, 2 pi over 4, 3 pi over 4. Now I'm going against my own word. I told you guys a minute ago don't do this, but I'm doing it, and that's okay. If you're going to graph more than one full period, that's perfectly fine. So we have vertical asymptote at pi over 4, vertical asymptote at 3 pi over 4. This x value is going to be halfway between pi over 4 and 3 pi over 4, which is 2 pi over 4, which is pi over 2. Now here's what we have not done. What's halfway between 1 pi over 4 and 2 pi over 4? It's going to be 3 pi over 8. How do I know this? I don't know. It's a very American phrase. We do not say, I do not know. We say, I don't know. It's all one word. I teach this to my students who are learning English as a second, third, fourth, fifth, sixth language. Okay, so we have pi over 2 and 3 pi over 4. So that's 2 pi over 4 and 3 pi over 4. Halfway between that is 2.5 pi over 4. I don't like that. Is 5 pi over 8. What in the world did you just do? I don't know, but I'll let you do that scribble off to the side. Remember, pi over 4 plus 3 pi over 4 divided by 2 gives us pi over 2. Pi over 4 plus pi over 2 divided by 2 gives us 3 pi over 8. Pi over 2 plus 3 pi over 4 divided by 2 gives us 5 pi over 8. Okay, and you can space this out and hand draw this all you like. I use the grid. You don't have to use the grid. Sometimes I use the grid, sometimes I don't. It's a cotangent function, so we're going to go down a value of a, so to the right, and down's really pi over 8. So I'm moving over to the right and down 1. There's a point there. The curve does this. And then to the left, really it's pi over 8, but to the left 1 interval, and up 1. So let's label the y-axis. So remember, label the y-axis here. Don't label the asymptotes. That gets really strange. It's not wrong. It's just unconventional. Anytime something's so strange, it can just be confusing. So try to make sure you label the x-axis with respect to 0, and try to make sure that you label the y-axis with respect to 0. The labels should all be, so for example, pi over 8, 2 pi over 8, 3 pi over 8, check, 4 pi over 8, 5 pi over 8, 6 pi over 8. You don't have to do all of that, but you do need to understand that. All right, so there is my one full wave of my cotangent function, one full period. Now the period of this function is I just realized I made script a boo-boo right here. Pi plus pi over 4 is not 3 pi over 4. And I noticed it when I decided to label the period. And this has a period of pi over 2, but wait, no, it has a period of pi. So, I'm going to pause it. I'm going to rework it at lightning speed, and it's going to be much simpler to navigate. But I will say this, it is nice. This is me finding a silver lining. That's what I do in life. You make a mistake, you're like, oh no, but then I got to practice over here finding all these crazy fractions. I'm going to chalk it up to experience, and I'm going to blast through this example to finish this up. Let's fix it. It was 0 to pi, all good. Add pi over 4. Pi plus pi over 4 is 5 pi over 4. Now, I don't like the graph. Let's do it by hand. So let's delete. So by hand, grid paper is nice, but that's all right. So I know pi over 4 is my first asymptote. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 is my second asymptote 1, asymptote 2. All right, the function was y equals cotangent of x minus pi over 4. So I know my a value is 1. So from the center, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, or pi, 2 pi over 4 or pi over 2. Boom, halfway. Now cotangent to the right and down one space. So I draw, and then one space up. And that's it. 1, 2, 3 exact points. And my asymptotes, I have my 5 labels on the x-axis, 2 labels on the y-axis that relate to A. All right, so you should feel pretty comfortable graphing any tangent function, any cotangent function, and of course at this point you go to practice and make sure you're careful now. We'll be doing lots of presentations in our next class, some of the spillover from our last class. So I reminded you, if you did not present at our last class, you'll present, and then we'll present some tangent and cotangent functions. Be safe, keep working hard, and I will see you in the classroom soon enough.